Hello, in this video I am going to explain ready shock tube and also the conservation of mass, momentum and energy which comes under module 1 and also the extended part of shock waves. So in this module I am going to take up ready shock tube. Ready shock tube is a hand operated shock tube capable of producing shock waves by using human energy. So it is a long cylindrical tube of about 100 centimeter in length and consists of two sections. These two sections are separated by a paper diaphragm. Now I am going to explain the construction part of ready shock tube. So ready shock tube is a cylindrical stainless tube of about 30 mm in diameter and of about 1 meter in length. It is divided into two sections, each of length 50 centimeter. One is driver section and the other one is driven section. So these two sections are separated by 0.1 mm thick paper diaphragm. So ready tube is fitted with a piston at one end, that is in the driver section. The other end is totally closed. The digital pressure gauge is mounted in the driver section closer to the paper diaphragm, that is you can see in the picture, and two piezoelectric sensors S1 and S2 are mounted at a distance of 70 mm apart and fitted closer to the downstream end or closed end of the ready tube. The driver section is filled with a gas called driver gas and the driven section is filled with a gas called test gas or driven gas. A port is provided in the driven section for filling test gas. Next I am going to explain the working, how the ready shock tube works. So ready shock tube is worked by pushing the piston hard into the driver tube until the paper diaphragm ruptures. Once the paper diaphragm ruptures, shock waves are produced. The produced shock waves pushes the driver gas into the driven section and which is moving towards downstream end. The generated moving shock waves that are traveling across the length of the driven section. The generated shock waves are instantaneously raise the temperature and pressure of the driven gas. The propagating primary shock waves are reflected from the downstream end. After the reflection, the test gas undergoes further compression, which boosts its temperature and pressure to still higher values by reflected shock waves. Actual creation of shock waves depends on the properties of driver and test gases and also the dimension of shock tube. Pressure rise caused by primary shock waves and reflected shock waves are sensed by sensors S1 and S2. Okay, so these two sensors are connected to digital CRO or cathode ray oscilloscope. Next, here I am going to explain or show you the chart which consists of two signals produced by sensor 1 and sensor 2. The signal which is in red color produced by sensor 2 and the signal which is in blue color sensed by sensor 1. So here it is possible to calculate the time taken by shock wave moving from sensor 1 to sensor 2. Let x be the distance between S1 and S2. Let delta t be the time taken by shock wave moving from S1 to S2. Then it is possible to calculate the velocity of shock wave given by x by delta t. And hence it is possible to calculate the Mach number which is equal to velocity of shock wave divided by velocity of sound. So in the next slide I am going to explain the characteristics of ready shock tube. Ready shock tube operates on the principle of free piston driven shock tube and it is a hand operated shock tube and it is capable of producing Mach number exceeding 1.5, and here the rupture pressure is a function of the thickness of the diaphragm, and the temperature exceeding 900 Kelvin can be easily obtained by reddish active. So these are all the characteristics of reddish active. In the next slide, so here I am going to explain the applications of shock tube or shock waves. Applications of shock waves. So for the first one is kidney stone treatment. So shock wave is used to shatter the kidney stones into smaller fragments, after which they are passed out of body smoothly through the urinary tracts. Shock waves are also be used to inject drug without using needles. So drugs can be injected into the body without using needles. The drug is filled into cartridge, kept pressed on the skin, and shockwave is sent into body using high pressure. The drug enters the body directly through the porosity of skin without any pain for the patient. And the third one is treatment of dry borewells. Shock waves sent through dry borewells for clearing the blockages, and finally it will rejuvenate the dry borewell into water source. So these are all three applications of shock waves. In the next slide, so here I am going to explain the law of conservation of mass, momentum and energy. So now let us consider a shock wave which is propagating with a speed w in a shock tube. The conditions of the shock wave at the downstream end can be determined by solving equations for conservation of mass, momentum and energy as applied to the shock region. These equations were also considered as Rankine-Hugoniot equations. Now let us consider P1, ρ1 and H1 be the values for pressure, density and enthalpy of the gas before the creation of shock waves, and P2, ρ2 and H2 be the corresponding values after the paper diaphragm ruptures. Let U1 be the velocity of the gas in front of the shock waves and U2 be the velocity of the gas following the shock wave. So by making use of these data, it is possible to explain the law of conservation of mass. So it states that the total mass of any isolated system remains unchanged or constant and is independent of any chemical and physical changes that could occur within the system. So we have an equation related to the law of conservation of mass, that is ρ1 u1 is equal to ρ2 u2, and by considering the law of conservation of momentum, so in a closed system the total momentum remains constant, or when two bodies collide in an isolated system the total momentum of the objects before collision equal to after the collision. So here the equation corresponding to the law of conservation of momentum is P1 plus ρ1 u1 square is equal to P2 plus ρ2 u2 square. So this is the equation corresponds to the law of conservation of momentum. Next, the law of conservation of energy. So it will states that the total energy of the isolated system or closed system is constant and is independent of any changes occur within the system. So the equation corresponds to the law of conservation of energy is H1 plus U1 square divided by 2 is equal to H2 plus U2 square by 2. So these were all the supporting equations for explaining the law of conservation of mass, momentum and energy. Okay, thank you.